Good afternoon, everyone. Hope you guys all had a nice weekend. Welcome to Lecture 7. So in Lecture 7, we're going to talk about manometry. Manometry is a common, probably a more classical type of pressure measurement, and it relies on the concepts of hydrostatics, which we reviewed last lecture. Here's a review of what we did last lecture. So we're going to begin the lecture now, okay? Thank you. Review of what we did last lecture. So we talked about hydrostatics. We defined an isobar, which is a line of constant pressure in our fluid. We can draw that in hydrostatics as horizontal lines. We talked about specific gravity, which is a way that we measure density relative to the density of water. We talked about through a derivation of F equals ma for a fluid with certain assumptions, which are that we have a static fluid with no acceleration. The pressure gradient is directly equal to rho times g, so that's a vector equation, and it tells us that the direction of pressure change is aligned with the direction of the gravitational field. So in other words, say for a cup of water, if the gravity field points down, the pressure gradient is aligned downward. We then integrated that equation to derive the equation shown there. So as you move downward along a line in a static fluid of constant density, the pressure increases linearly with depth. So that's P equals P0 plus rho gy. P0 there is the pressure at y equals 0. We'll see that that's the more general definition today. So last lecture I said you can say P0 equals 0, and that'll give you gauge pressure. That's kind of assuming you have atmosphere at the top of your fluid. We'll have a better understanding of that today. Context again, this is all within hydrostatics still. So this lecture and the next lecture are still all going to be related to hydrostatics, and then we'll get into the rest of the forces later on in Module 2. So the concepts today are, we're going to apply the core concepts from hydrostatics to manometers, which are a pressure measurement device. We're going to define Pascal's law, and we're going to compute pressure measurements using a manometer. Are there any questions before I begin the notes today? Okay. I'm going to start off by defining Pascal's law because we're going to use it quite heavily in this section. So Pascal's law says that within the same connected fluid, two points at equal height will have equal pressure. So it doesn't really matter how the fluids are connected. It could be connected through a tube, but they have to be connected. So say you have a big tank of water here and a big tank of water here, and all that's connecting them is a tube. Still a connected fluid, so assuming that flow in both tanks are static, the pressure at, say, height here in this tank will be the same at the same height in the second tank because those fluids are connected. And that P equals basically rho gy allows us to calculate that pressure from a free surface. So P equals P0 plus rho gy. I'll talk again about P0. So P0 is not always atmospheric pressure. More generally, it's just the pressure at y equals 0. So in the derivation where we derived this equation, we needed to know, we integrated from basically y equals 0 to y, and the P0 is the pressure at y equals 0. You'll be a little bit more comfortable with that after we do some examples related to manometry. So here's an example. It's from the textbook, so that's the white textbook. So I'm going to draw this schematic here. So we have flow through a pipe or a channel or something like that here. Say flow of, I guess, some blue fluid. And that blue fluid is connected to a pressure gauge through a series of tubes here. So in case you hadn't guessed, this diagram is not to scale, but that's good. So let's say we have, so this I haven't drawn, I'm not going to draw the lines, but these are basically tubes with these three different fluids in them. And I'll give you some height differences here. Okay, and then I'll take a point there, 6 centimeters. Okay, so the fluids here have three different densities. I'll give you the densities. So the fluid here, the blue fluid has 1,000 kilograms per meter cubed. The gray fluid is 13,567. The light blue fluid is 997. We don't know what these fluids are, and it doesn't really matter, so I'm going to call these the mystery fluids. So this is the problem statement here. The problem is, so for point A and point B, so B is at the center of that gauge where the 6 centimeters is defined to. So the problem is gauge B is used to measure the pressure at A. So if we have, say, some sort of pressure sensor there, if the pressure at B is 87 kilopascals, what is P? So we know basically the pressure at point B, and we need to determine the pressure at point A. And we know the pressure at point B by some sort of gauge measurement. So you can assume it is going to be a gauge pressure. Any questions on the problem statement? If you guys can't see like something on the projector, there's much less contrast on the projector than there is here. So if something's unclear, just let me know and I can mark it. No questions on the setup? Okay, good. So the solution is we're going to start at a known pressure and then work our way through each of the three different fluids to get to point A. So start at B, work our way to A. So I'll define some separate points here. So point 1 will be this dark blue gray interface. Say point 2 is there. Point 3 is there. Point 4 is, that point 4 is actually in line with the plate. So zoom in just so you can see clearly what these points are. So we can, since we know the pressure at B, we can calculate the pressure gain from moving downwards in fluid, in the blue fluid to point 1. Now we're switching to different fluids, so our fluid properties will change, but we can again calculate the pressure gain from there, from 1 to 2. So 2 is at the same level as here, so there's not going to be any pressure difference as we move across here. So we can go to 2, and then go from 2 to 3, so that's going to be moving upward, so the pressure will decrease. Then our fluid properties will change, and we'll go from 3 to 4, and then since 4 is the same level as, say, point A, it's going to have the same pressure as point A. So you can assume that even though the flow in A is moving, the pressure along that line is the same as pressure at 4. Yes, please.
Step 1, step 3.
Yeah. So that's another way I'm going to solve the problem after. So what we're going to do is go down and then across and then back up, and I'll show that it's equivalent as basically going to this line. Since this is a connected fluid, the pressure here is going to be equal to the pressure here. I'm just going to show you that. Any other questions about the problem or how we're going to solve it? Okay, so let's go from B to 1. So P1, by the way, all these equations are going to be P equals P0 plus rho gy, and we're just going to change what those variables are. So P1 is PB plus rho g, and I'll say y b to 1. So that's 87. Okay, so just so you can look to see where those numbers came from. So we know that fluid B, has a density of, I think I got our mystery fluids density. So it's actually dark blue that has that 997. It's not going to make much of a difference. But... Okay, so the dark blue fluid is a 997, so we're just going to move downwards 6 centimeters in that fluid, and you can see we gained about 0.59 kilopascals by doing that. Are there any questions on where any of those numbers came from? It's just keep track of the units, so I'm using like 10 to the 3 for kilopascals, 10 to the minus 2 for centimeters. I find that easiest to just do it that way. Any questions on where any of those numbers came from? Okay. So now we know the pressure at point 1. So now we're going to go from 1 to 2. So P2 is P1. That's rho g by 1 to 2. So we calculated P1 as 87.59 kilopascals. So we're going 11 centimeters downward in the gray fluid, which has a very high density of 13, basically 13,500 kilograms per meter cubed. So that's basically mercury, I think. So we're going to pick up a lot of pressure gain from that. So if you just compare the densities alone, it's over 10 times more pressure gain you pick up from mercury for the same height as water. Any questions on where any of these numbers come from? Because that's kind of the hard part of this, is just getting the numbers right. Okay. So that's going to be P2 is 102.22 kilopascals. So we picked up like 15 kilopascals of added pressure. Okay. 2 to 3. So 2 to 3, we're going to move upwards through mercury, or through the gray fluid, I should say. So we're going to decrease the pressure. So it's just a good gut check as you're doing this. If the pressure's got to decrease as you move upwards. So in that case, the decrease is accounted for by saying our y is going to be a negative y. So rho gy 2 to 3. So that's a negative 4 for moving upward. It's going to be 96.9 kilopascals. Any questions on that one? I'm going quite slow just to make sure we have the understand where all the different numbers are coming from. So if you're confused at any of the numbers at the negative, please let me know. This is basically as simple as it will get. Get. 3 to 4 now. So P4 is P3 plus rho g y 3 to 4. So I'd say probably the biggest error that I could see you guys making for a question like this are just the units. So keeping track of your like 10 to the negative 2 and 10 to the 3. So like for example, the 96.89 came out as 96.9 times 10 to the 3, and then I just wrote kilopascals. So just be really careful with your units. Okay, so that's going to be a moving upward through a fluid of density 1000, which is what the light blue fluid has. Scroll back up. So that's where that 5 came from here. And the density of that fluid is 1000. So if we make the assumption that P4 is basically PA, then we calculate PA now. So 96.4 kilopascals. So yeah, as one of you pointed out, we can skip one of the steps here. So we can skip having to go to point 2. I'm going to just draw a diagram here so I don't have to back up. So the schematic was kind of like this. So what we did, just as a review, is what we actually did in the problem was we started at here, into here, into here, then applied Pascal's law to go straight across here, and back up, then here, and then Pascal's law again. So that's the route we took. But since all the heights were given, we would have saved a step if we had gone like this, so the red route. So since we know the height difference, here, we don't have to go like back. We don't have to go down through the fluid and then back up through the fluid. We can just say the point here has the same pressure as the point here. So if you calculate that pressure by moving this depth, you've calculated the pressure on that side. Any questions on that? So I'll kind of leave the verification of that up to you, but you can see that either way you use to calculate P3, I believe is the point number. Either way you use to calculate P3 will work. So I'll give a very dramatic example of this. Let's say we have some fluid here. And some green fluid here. And these fluids are connected by some red fluid that does this. All that matters is the height difference. Say we're trying to go from here to here. All that matters is the height difference between those 2 points. You don't have to go through every single length of tubing to get there. So the only thing that matters in this problem is this height h. So if I give that to you on an exam, I highly recommend going, straight across. So again, the core concept here is that all you have to do is calculate the pressure. All you have to do is calculate that small amount of pressure gain there, and then you can move horizontally. Because those points are at the same height and the same connected fluid, you can move directly straight across. Sorry, my massive drawing is hurting OneNote's feelings. Okay, so yeah, you can move. So any questions about that? That's Pascal's law in action there. Yes, please. Yeah.
Is it assuming that there's like a boundary who's preventing the two liquids from combining?
Yes, that's a good question. Yeah. Yeah, so that it's kind of implicit in this question. We've assumed that the fluids are immiscible, so they don't mix. So if they start mixing, then they kind of become the same fluid. Assuming they're completely mixed, you could say the density would have changed, but that's not something you ever have to deal with in these hydrostatic problems. You assume it's kind of immiscible and there's a clear boundary between the two fluids. Any other questions about Pascal's law? I'm going to do another example now. So a mercury manometer, which is quite common. is used to measure air pressure inside a tank. So I'll give you the measurement in the diagram. So the question is what is the gauge pressure in the tank? I'll also give you the mercury specific gravity, density of water, and I'll tell you what G to use. So we have some tank here that we want to know the pressure in. And in order to do that, we basically have the air inside this tank push on a column of mercury. You measure the height change of that column of mercury in order to calculate the pressure in the tank. So pretend that this tube here, this is called a U-tube manometer, by the way, the original U-tube. So assume that this is filled with mercury. We have usually some sort of like gradations there, so we can actually measure the height of that. So say I tell you that the height difference between these 2 points is 300 millimeters. So in gauge pressure units, then we can say P0. So we're going to move basically from here to here in the mercury, and then assume that there's constant pressure as we move in air. Like I said, we can usually neglect the hydrostatic head of air because the density is so small. So the gauge pressure P is just going to be rho gy of mercury, so 13.6, which is the specific gravity, times 1,000. So that's going to be 40 kilopascals gauge. Just to clarify that we're using gauge units. So any questions there? So what I've written down is basically just the path here. That's just rho gy and mercury. But implicitly what we've kind of done is done this. So we went to there, then moved across, then we moved up. But we neglect the movement through the air. If I tell you the tank's filled with air, you can neglect the hydrostatic head of air. It'll be so small. Another interesting thing about this example is it actually tells us about a common pressure unit. So we calculated this in kilopascals, but actually this is exactly equivalent to 300 millimeters of mercury. So you might see mmHg. So in case you're wondering like why people use that pressure measurement of millimeters of mercury, it's because they're literally reading millimeters of mercury on something like this. So that's where those come from. So like you have inches water gauge is another unit. It's common, or like inches of mercury. So these, if you go into Google and type, 40 kilopascals to millimeters of mercury, you'll get that they're equivalent. So that's basically what we've done here. Any questions about that example or those pressure units? So again, that allows us to convert a length of a liquid into a pressure. I'm going to do a third example now. Maybe maybe someone can, maybe you've seen manometers before in practice, but does anyone have an idea about if we wanted our manometer to be very highly accurate, how could we increase the accuracy of our manometer? Let's say we wanted to measure this pressure here. How could we increase the accuracy of the manometer? So say we wanted to measure this pressure, say we're measuring it right now at plus or minus 1 kilopascals. How could we increase the accuracy of that? Yes, maybe Aaron. Yeah. Okay, Aaron can go first. How's that? Yeah.
Um, so when a fluid's in a cylinder like that, it kind of like comes up a little bit at the
Mhm.
edge. So if you change the diameter of the tube, would that help? I'm not sure
Yeah,
which
that's a good point.
direction.
Yeah, so an issue in reading manometers is that you kind of get that. So that's actually due to surface tension. So you could, yeah, you definitely like adjusting the tube diameter here so that that's easier to read is something you could do. Yeah. Did you have another idea?
Pulling a vacuum on the
Pulling a vacuum on the open side. So I guess how would that help our accuracy in this case?
I guess instead of neglecting the air pressure, I think we just like eliminating.
So in this case, we haven't really neglected the air pressure. We've assumed that we want gauge pressure units. So at the top of the mercury, we're at zero pressure gauge. So yes, please. Yes, you incline it. So that's the answer I was looking for. So what happens when we incline the manometer? So what we're trying to do here is trying to measure a length, right? So this example, we're going to see why we incline manometers a lot of the time in practice. So manometers are often inclined. Reduce, say, the measurement error. So I'm going to say determine something that characterizes a manometer. So I'll call this the Pascal per meter measured as a function of theta. We'll find what theta is here. Say we have something we're trying to measure. So this is what an inclined manometer looks like. So what I mean by meter measured is ultimately the thing that affects the hydrostatic head is the height difference between these 2 points. But what we usually do on manometers is we place the gradations like this. Then when you measure basically a length, so that length would be from here to here. I'll draw a triangle just to be clear. I'm going to say theta is that angle there. So the actual thing you measure when you read this is that length L. But the thing that produces the hydrostatic head is, of course, H. It's not the length along the manometer, that it's the actual height change. Okay. So say theta was 90 degrees. That's where you get your straight U-tube manometer, which is something like this. In that case, you're measuring here. So that's basically L equals H. So the length you measure on your manometer will be equal to the height change in the fluid. So we can use our relationship here. So the change in pressure between these 2 points will be delta P. So the 2 points I'm talking about are here and here. These laser pointers. So that point and that point. So delta P is rho GH, which is rho G L sine theta. So delta P over L is rho G sine theta. Of course, this is valid for a specific range of theta. So usually inclined manometers look something like the figure I've drawn above. Let's say we're trying to measure a pressure here of delta P of 100 pascals. So that's roughly like 0.1% of a typical atmospheric pressure. Just to give you an idea of, it's relatively, your instrument has to be, half decent to do that. But the pressures we try to measure with these get much smaller than that. So with the angle theta, let me give you a table here. So theta of 90 degrees, 60 degrees, 30 degrees, and 10 degrees. So this is basically like a U with a bit of a angle, even more. So those are what this inclined manometer might look like. So say we're trying to measure that pressure difference of 100 pascals. So we would read an L on that manometer of 1 centimeter, 60 degrees, 1.2 centimeters, and 2 centimeters, then 5.8 centimeters. So even though the H in all these cases, the actual height change is the same because the pressure change is the same. The actual length that you'll measure as you look at it will grow, which allows your measurement to be better. Because your length measurement, say you're limited by gradation of like 0.5 millimeters or something like that, the relative error decreases the longer that gets. So again, this L is the actual length that you measure. Like as you look at the manometer, you're measuring this length here. But it's the H that creates the pressure change. So I'll give a relative, so I'll say percentage error in that pressure difference. So this is with, say, the error in your length. You can estimate your length to like plus or minus 0.5 millimeters. Say you don't have that good of a ruler, or this is just to illustrate how much benefit you actually get from the inclined manometers. So you can go to plus minus 0.5 millimeters. So you get a relative error in your pressure there of 5%, 4.2%, 2.5%. And at 10 degrees, you go down to 0.85% error. So manometers are actually still used in labs, believe it or not, to when you have to measure something with a relatively high accuracy, a relatively low uncertainty, I should say. Are there any questions about that? So maybe, does anyone have an idea of like a disadvantage of using a manometer to measure pressure? Let's say compared to an electrical pressure transducer and a manometer. I think you had your hand up first, so you can go.
I mean, there are a couple with electric ones that could have like static like measurement noise, but with like the fluid one, I guess you get one uniform measurement.
Yeah, okay, so you don't have to deal with electrical noise.
You're only getting that one point.
Yeah, that's a good idea. So you're saying you don't have to deal with electrical noise, you're just kind of measuring a length. Right? So it's easier. Is that is that about right? Okay, maybe Ian?
I mean, one downside of pressure manometer is it could be very large if you're trying to deal with larger pressures.
Yeah.
Especially if you're inclining it, you can start going a long way out.
Yeah, they can get pretty big. So that's why mercury is often used in barometers because it has such a high density. So you have to measure a high pressure change. You want something with a really high density. So that way you're actually, the height is less for the same pressure change. So manometers usually aren't used to measure things that have dynamic signals. So I'll show a video now here, but they don't have a very good like time response. So as that pressure changes, the fluid actually kind of oscillates as it balances itself out. So that's the main area that manometers aren't used in. But I do have some videos so we can look at.
Here.
So this
Nothing
is a demo of
too crazy. I've got an open end tube here, and you can see their levels were equal.
So he just has like a syringe attached to, this is kind of a, so there's a U-tube manometer there on
The
YouTube.
amount of gas that's
There's
trapped
a
in
syringe
this
attached
area.
to this, and it's just
So
filled
by
with
me
fluid.
making the space of the volume smaller,
As he kind of like
okay,
squeezes the syringe,
the
pressure
pressure is
increases.
going to increase. So I am going to, Boyle's law, lower the volume by forcing the gas molecules into a.
Yeah, and his Boyle's law. So he kind of like pulls on the syringe to create a relative negative gauge pressure inside the syringe. So that's why the pressure here, that's why the height here is lower than the height here, because this pressure is, so that pressure difference there is going to give you the negative gauge pressure inside the manometer. And what I was talking about the time response, you can see as he kind of loosens the syringe to bring it both sides back to atmospheric pressure, you can see how much
Smaller
delay there
space is going
in
to
that
increase the
measurement.
pressure.
So that
the manometer
kind of
is going to measure that increase in pressure. When the pressure was equal,
watch here the two sides, they
when the
oscillate.
pressure was equal, these levels
So if you're trying to measure
equal,
a step change in pressure, you need to
because the pressure in the inside of this tube is equal to the pressure.
I'm not going to play the whole thing, but you can go watch that on YouTube. It's actually a pretty good demo. I'll give an example now of, so they actually did used to use manometers, like you said, in the wind tunnel to measure pressure. So what they would do is they still use manometers in a lot of wind tunnels that are.
Means of determining pressure difference.
So they're basically just explaining in this video how we can take a height change and measure a pressure difference, which by now we've spent 2 lectures on, so you guys understand that. But I'll show you what they do.
Additional tubes may be added,
So
each connected to a different value of pressure, and each will indicate that pressure accurately,
and this idea,
regardless of pressures in the other. Operating.
So that is a bank of manometers. So I don't know how many are there, but that's a lot of different manometers. So all those lines are tubes filled with, I'm not sure what they used here, maybe water or something. So they use that to measure the pressure change. So you can connect each of those manometers to a different spot on your test geometry. And you can measure pressure distributions that way. So at here,
Pressures along the surfaces are at such
all the
values
tubes coming out of this airfoil are connected to different parts of the
as
manometer.
would be met under flying conditions.
So that's, for example, I think you can see the pressure changes in each of those tubes. So if you know where each of the tubes goes to, then you can calculate pressure distributions used by measuring the
The
manometer.
manometer tubes tell the story. Levels fluctuate slightly as minute variations in airspeed or density occur, but the ratios are constant, and the position of the liquid in the tube shows both positive and negative values for the airfoil. The tubes are
So they take a picture. This is, by the way, a lot of the airfoils used on modern planes were designed and originally tested this way. So they take a picture of this bank of manometers, and then they measure the height of the picture,
photographed
calculate the
to assure simultaneous readings of all tubes, and the photograph is used by engineers to plot the pressure curve.
So then basically you have pressure measurements. So that's, just to clarify, the tubes are connected to all the different points along the airfoil surface. So you've measured the pressure at the surface, but you're going to plot kind of a distribution of pressure over the airfoil. And that's what a typical like pressure distribution looks like. So you have the top of the airfoil is the suction side, so that's going to be a negative pressure. And the bottom is positive pressure, but they usually draw it like that.
Positive pressures are shown in black.
So that's
negative.
That's basically how they used to measure airfoils. I think sometimes when you need really highly accurate measurements, you can do that. And like I mentioned about the time response, the flow is usually steady for flow over an airfoil, so you're not worried about that time response issue with the manometers. So if you take an instantaneous photo, you can assume steady in that case. So are there any questions about this? If you're interested in watching these videos, I've posted them online as well. Okay, if there's no more questions, that's everything for today. Thank you, everyone.